Hey dudes, Dude the Builder here. In this episode of Zig and Death, we're going to be taking a look at some metaprogramming tools in Zig, specifically the ones that you can find in the std.meta namespace. But first things first, I gotta give a big thank you to Robert Farrell and Brian Bonsignore, who made donations to the channel. I really appreciate it. Thank you very much. This really helps a lot. And anybody that wants to make a donation to the channel can find a link in the video description and in the channel homepage. So Robert Farrell and Brian Bonsignore, thank you very much. Basically in Zig, when we talk about metaprogramming, we're also implying that we're talking about comptime, because practically all of this that we're going to be taking a look at is happening at compile time. These are a lot of functions that we're going to be working with that can only be evaluated and executed at compile time, because we're dealing directly with types, as you will see. So let's jump right in. Here I have an example of an enum, basically a tagged union. We have here, we're using the union enum here syntax, and we only have two fields for this union, tagged union, an int and a float. And we have this function here called is, which will let us, when we have an instance of this tagged union, we can call this as a method. What we want to do is, if we pass in an enum literal, we want to know if this instance of this tag union is of that type. But usually this parameter here, tag, is going to be one of these two variants of the tagged union, int or float. And to be able to define this function signature here, we have to know the type of the tag of this tag union. So instead of having to define the enum separately, so we can then have that type that we can use here in this type for this tag parameter of this function, we have at our disposal in the std.meta namespace the tag function. And as you can see, it has a capital T, and that's an indicator. Whenever you see functions that start with a capital letter, these are functions that return a type. So tag is going to return the type of the tag of a tagged union. And that's exactly what we need for this parameter. So we pass in the type of the tag union, which is number, and this will return the type of the tag of this tagged union. This will become clear when we see an example of the usage that we have here in our main function. Here we are defining this variable called num, and it's of type number, the type tag union type. And in this case, we're using the int variant and setting it to 42. And now we can use our function here, our method is on that instance of the tag union, and we can test by passing in this enum literal.int if that's indeed the tag of the active field of this tag union. And we can do that thanks to that std.meta tag function. Here we're now reassigning to this instance of the tag union. This time we're using the float variant, and we're setting it to 3.1415. And once again, we'll be using the is method with this time the .float literal. So this is really convenient. It lets us extract from a tag union that uses an anonymous enum as the tag type. we can extract that type from that tag union, so we can then use it in function signatures and things like that. There's another handy little function when dealing with tag unions that's called active tag in std.meta. And as its name suggests, it's gonna basically return which of the enum variants or the fields of the enum is the one that's active. And here, in order to print that out as a string, we're going to be using the built-in tag name. So whatever we receive from meta active tag here with our instance of the tag union number, we're going to turn into a string with that tag name. So let's go here to the terminal and run this program. Here we have the results of using our is method here. Okay, we have true in both cases. And here is where we have the question of which is active, and it says that indeed it's the float, because that's the one, that's the last one that we set for that instance. Okay, so that is working as expected. Next, we're going to have a little tool here that's called string to enum. And this can pop up frequently, the need to turn a string. Maybe you're getting a string from somewhere else and you need to convert that string to an enum. Well, you can use the string to enum function in Meta to do just that. Here we're going to be obtaining, once again, we're going to be using the tag function to obtain the type of the enum tag type of the tag union, and we're saving that in here in this constant called number tag enum, and then we're going to be using that to test basically. Here we're testing if what we obtain from calling string to enum here, we specify the enum type, which is that type of our tag union, and we're specifying the string here. This is the string that we want to convert to one of the variants of that enum int here, and we're going to be testing precisely if that's equal to the variant directly that we're specifying here literally in the source code. And if we look at the output over here, in effect, yes, it says it's true. The number.int is going to be equal to the conversion of the text, the string int, to an enum variant. Okay, so that's working as expected too. Next up, we're going to look at meta.child. We can have the situation where maybe we're passed in a sequence, anything that can have a child type within it. For example, if we have slices, we have elements of a certain type, an array, and also pointers or optionals. Well, we can use this child function in the meta namespace. Once again, it begins with a capital letter, so it returns a type. So here we want to know what's the child type of a slice of const U8. Well, that's supposed to be precisely a U8, okay? And in the case of an optional U8, the child would be the U8 once again. So let's take a look here in the output. And as you can see, effectively, the child type is U8. And here, in the case of the optional, we have also that the child type is U8. So that can come in handy too. Next up, we have meta.sentinel. And this will let us convert any type of sequence that doesn't have a sentinel to a sentinel terminated version of that sequence. So in this case, we're going to be testing this out with a slice of const U8. And we're going to be using that sentinel function here. Once again, you see it starts with capital letters, so it returns a type, a new type. The type that we're passing in as the original type is the slice of const U8, and we're saying that we want to use as a sentinel 0. it's implied that this sentinel value that we're passing in here has to be of the type of the elements of this other original type. So let's go to the output, and as you can see, it converts the slice of const_u8 to a terminated zero terminated sentinel slice of const_u8. Okay. Next up, this is directly related to our episode about memory layout. We have here a meta.container layout, and with this you can detect what the actual layout, the memory layout of a struct that's passed in. So we have the different layouts that we discussed. For example, the Zig native automatic layout, which makes no guarantees about field order and things like that. We have also the extern memory layout, which basically complies with the ABI, the C ABI, and does guarantee the order of the fields. And we also have the packstruct memory layout, which basically removes all the padding from the fields. Is a more compact representation in memory. And we can detect all of these using this meta.container layout function. So let's look at the output here. And as you can see, here when we have a normal Zig struct, the layout is going to be auto. When we have an extern struct, it tells us indeed it's extern, and for a pack struct we have here packed. Okay, so with container layout we can detect that at compile time if we're passed in a struct. Next, we're going to be taking a look at the fields function. Fields can come in really handy when we're dealing with structs, because it lets us basically obtain a sequence of the fields of a struct, or any other type that has fields. For example, we have also enums, unions, or even error sets. So here, for example, we're going to be calling the fields function on this anonymous struct that we have here with 3 fields. And then we can iterate over that sequence that we obtained using a for, but this time it has to be an inline for, because we are dealing with comptime only values here. So it has to be an inline for. And then those fields that we obtain themselves, they have different fields, of which we're going to be using here the name and the type, okay, to print those out. And as you can see here we go. We have A, it's telling us the type is U8, name of the other one is B, it's a U16, and C, it's a F32. So with fields, we can obtain the fields of these different data types, and we can iterate over them if we want. Here we have meta tags, and with meta tags, we can obtain an array of the different variants in an enum or an error set. So this is more specific to enums or error sets. In this case, we're defining this enum right here directly with ABC. And then we're going to be basically printing out the third item of this array that we're going to be obtaining. Once again, converting the name to a string with the built-in tag name. So as you can see here, it says that tags2 is indeed the C variant of that enum that we passed in. Here we have an interesting function. This one is called field enum. And what this does, we saw that fields returns like a slice of the fields of a struct. Here we are generating an enum with the fields of the struct. So here, for example, we have this struct that has, once again, the 3 fields A, B, and C. And here, as you can see, instead of using the indexing operation that we used here with the square brackets, we're directly using here a dot, because this FE is indeed an enum. So it's going to have variants for the different struct fields. In this case, B, we're testing out by using here the tag name to convert it to a string, the B variant of that enum that was generated by meta.fieldEnum. And here in the output, as you can see, indeed, here we have that fe.b is indeed B. Okay. Now, next up, we're going to have the meta.declarenum, and this basically does the same thing, but for the declarations. Remember that inside a struct, an enum, a unium, these are namespaces, and you can have declarations inside, and declarations can be, for example, constants and variables and functions. So in this case, instead of having fields A, B, and C, we have these three constants. We're declaring them. In order to be visible to this function, declarenum, they have to be public, okay? So we make them public. And now here, we're going to be querying basically that enum that we returned once again, the B variant, and converting that into a string. And as you can see here, that result, the declarenum de.b, it indeed has a B variant. So that can come in handy. Here, we're going to be looking at the meta.equal. This is interesting because precisely using many of these tools that we have seen, the meta namespace provides this equal function that can test for equality of different types, but both of the arguments that we pass in have to be of the same type, which is expected in an equality test. So here we have this struct type called S1, and we're defining these two instances here, or three instances, S1, S2, S3. They're all of type S1. And S1 and S2 have the same values for the fields, and S3 is different because we have here different values. And we can indeed test here for equality using meta.equal. In the case of our instance S1 with S2, they should be equal. And in the case of S1 with S3, they should not be equal. So in the output, that's exactly what we get here. It's true here that they're equal, and it's false. Okay. Next up, we have meta.fieldIndex. And what this does is when you have a type that has fields and you pass in a field name, in this case we're passing in the name B, it's gonna give you the index of that field, and it's going to be the index relative to the ordering in the source code. Okay, so this doesn't have to do with the actual memory layout of the fields. It's the ordering as it appears in the source code. So in this case, B is the second field, so it should be index 1. And that's exactly what we see here. S1.b has index 1. Here's an interesting aspect of comptime metaprogramming in Zig, is that you can even create types, and you can create primitive types here. The function int in meta lets you create an integer type at comptime. Here we first have to obtain the size in bits, or the bit width of the integer type that we're going to be creating, and this has to be known at comptime too. So that's why I'm using here this comptime keyword to force this calculation here of the log2 to happen at compile time. So I'm using this studmath log2 int seal, and this will obtain the log2 of this number that we're passing in this case 1 million. And we are saying that we want to use the result type is going to be usize of this calculation. And then we print out what we obtained from that calculation here, the bits. And then here we're using the meta.int to construct an integer type. We're telling it that we want it to be unsigned, and we pass those number of bits here. So the result of this meta.int should be an integer, an unsigned integer with the bits equal to these bits that we obtained in our log calculation. And if we go out here to the output, we see that the bits required to represent 1 million is 21. Okay. And when we actually construct the integer, that's the integer type that we finally obtained. It's a U21. So this is correct. There's also an analogous float function that lets you create a floating point type. Here, finally, we're going to be looking at meta.isError. If you have an error union, here we're defining maybe error as an error union of any error U8. And we are assigning it here the error, not a number. And with isError, you can detect if indeed that value is the error variant of that union. Okay, so here this should be true. Then we set it to an actual U8, so it's no longer an error. And so in this case, it should be false. And as you can see, that's the actual output that we obtain. Okay, so basically that's what I wanted to demonstrate. The std.meta namespace has all these little functions and much more. There are more functions that you can make use of when you're doing comptime metaprogramming in Zig. It's basically a bag of tricks. So I hope you find this useful. Do the builder here. I'll see you in the next one.